Greetings! We began this course by taking a very macroscopic approach to observing chemical reactions and processes. This week we will zoom in dramatically to examine the electronic structure of the atom and how that structure can change in response to external stimuli. Eventually, this will lead us to understand why different elements emit different colors upon relaxation. If we could see an atom, what would it look like? Before we discuss this further, I think it is a good exercise for students to write down their notions of atomic structure. So think about your conceptions of the atom. What parts does it have, and where are those parts located? Are any of the parts moving? What adjectives would you use to describe the consistency of the atom? Is it hard? Is it soft? Is it squishy? Please go ahead and pause the video now. Then take out a piece of paper and sketch your diagram of the atom. Label the parts and write a short paragraph that describes the atom. I've completed this exercise many times with thousands of students. Now, if you've been in this class for the past few weeks, you've had a leg up on most of the people who I've had do this exercise because we've already talked a little bit about the subatomic particles. I've seen all kinds of pictures for what people think atoms look like. But the most common picture that I see drawn is something that looks like this. A lot of times, this is the model that people have in their mind for atomic structure. It is a core nucleus with protons and neutrons, and then orbiting that nucleus are the electrons. This type of drawing is very prevalent in descriptions of the atom. In fact, sometimes you'll see it even on the Atomic Energy Commission's seal. I actually have it on my class ring from graduating college. It's not the most accurate model, but it is a model that many people have. Maybe it's not what you drew, but it is something that a lot of people draw, so I thought I would show it here. We're going to continue talking about the structure of the atom and thinking about how accurate or inaccurate this model that is drawn here is. On the last slide, I asked you if we could see an atom, how would it appear? But before we do that, we need to ask an even deeper question, and that is, how do we see anything at all? Do you have ideas about how we are able to see? For example, can we see in the dark? Have you ever been spelunking in a cave? I did this as a child in Missouri. We would go in a cave and they had lights in the cave because these were tourist caves. But on a lot of the tours, the person leading the tour would turn off all of the lights. And you wouldn't be able to see anything, not your hand in front of your face or anything else, once you were down inside the earth without light. So we need light to see. If we're going to look at the atom, let's begin our discussion of looking at the atom by discussing the light that we're going to use to be able to see the atom. Many experiments in classical physics have shown that light is a wave. You probably know about waves from math. Let's suppose that we have two sine waves. These particular two sine waves are in phase. They have a crest and a trough. They start by going up and then they go down, and they both go up and down at exactly the same point on the x-axis. So each of these waves has a crest and a trough, and I'm adding them so that they are both in phase. If I added them together, what would the result be? Go ahead and take a guess at that now. Some of you know from math that if you add two sine waves that are in phase, the result is a sine wave with the same wavelength but double the amplitude. In other words, the crest is twice as high and the trough is twice as deep, but the distance from where the wave started to where the wave ended is exactly the same. This is called constructive interference, and this happens when waves add in phase. In other words, the crests align and the troughs align. What if I take two waves and I add them so that they are exactly out of phase? In this case, I have the trough of one wave aligning with the crest of the other wave. You can think mathematically about what would happen if you graph that. So you could draw a little axis like this, and you could say maybe this wave has an amplitude of +1 and it goes down to -1, and the same for the other wave. What would happen if you added those two waves up this time? Now they're completely out of phase. In this case, the two things that you would be adding would look like this. And at every point on the graph where one of the waves was going up, the other wave would be going down by the same amount. And they cancel out. This is called destructive interference. So waves can interact in different ways. They can interact constructively, which is shown on the top. Constructive interference. Or they can interact destructively if they're out of phase. And when there's destructive interphase, it's like there's no wave there at all. If you were doing this in a water tank, and I did that in high school physics, you would see that the water would just be flat where there's destructive interference. So we've determined that light, if it's a wave, can exhibit constructive and destructive interference. We can observe that by passing the light through a grating. A grating is a series of small vertical slits. This particular grating has 300 slits per millimeter. So there are these tiny vertical slits that the light waves are being passed through. What happens to the light on the other side? Well, let's look at a single beam of light. Let's look at a red laser. Let's pass the red laser through this grating and see what happens on the other side. Now this would be just like a red laser pointer. It should give us a red point if there's nothing between us and what we're shining it on. But if we put a grating between us and the wall, what we see is that the light gets split into several points. This is an illustration of light interference using a red light laser. This is a helium neon laser beam. And it's going through a diffraction grating which separates the light waves into areas of constructive interference. You can see they're brightest at these points. And areas of destructive interference where there's just darkness. Can you see that the light areas of constructive interference seem to be fairly equally spaced? I think there's one here actually that we can't see because we've got this corner in the wall. At this particular lab, they are measuring the distance between the points to help calibrate their laser. The reason that this happens is that light bends when it passes through any transparent material other than air, such as glass or water. This bending occurs because the light travels slower in the glass or water, because there it has to bounce off lots of particles of matter in its path. In air it doesn't have as many particles in its path, so it travels more quickly. In air it has a fairly clear path. Different colors of light have different wavelengths, and we'll talk about that more in a minute. We can see these wavelengths when the light is separated into its component colors, which are bent different amounts by either the grating or by the prism. Again, the grating has narrow slits with a periodic structure, which split the beam of light into multiple directions, where a prism, as you can see in this diagram, just separates the light by color but moves it only in one direction. Any discussion of the nature of light needs to include James Maxwell. Maxwell was a Scottish mathematician and scientist. He was a famous pioneer of electromagnetism, kinetics, and thermodynamics. He authored the Maxwell equations, which are named after him. He also developed the concept of dimensional analysis, which we use so frequently in this course. He was very interested in light, and in fact, he was the first to commission and direct the fabrication of the first permanent color photograph, which is shown here, this photo of a Scottish tartan. There are several things I enjoy about the story of Maxwell's life. One of them was that he was a devoted teacher. spending at least 15 hours a week lecturing. Some of that time was pro bono work at the local men's working college, which I imagine is the equivalent to today's community college, if there was such an equivalent at that time. He did that simply because he enjoyed teaching and not because there was any money involved at all. He also loved poetry, and he worked in the laboratory with his wife, Catherine, at a time when women very rarely were allowed to be involved in science. At one point in his career, he found himself in the unfortunate position of being laid off from his job. But he persevered and found an even better post, something to inspire anyone who has ever found themselves suddenly unemployed. One of the questions that Maxwell asked himself is, what is light? Now, he was able to go into detail and calculate the speed of light, which was already known, through a different method. And he determined that light is composed of oscillating electric and magnetic fields, which are orthogonal to each other. But the bottom line here is that light is characterized as a wave in classical physics. And waves can be characterized by different properties or different variables. One of those variables which is important to us is the wavelength, which is given the symbol lambda. Another variable that is used to characterize light is the frequency. In other words, how often does the wave come by us? So if I drew a simple wave up here, the wavelength would be the distance from the beginning of one crest to the end of one trough. So here I've drawn two wavelengths of light. And the frequency would be, if we imagine that this wave was moving in this direction, and we had our eyeball up here and we were looking down at it, and how often would that wave come by our eye? That is the frequency. If you think about waves in the ocean, the wavelength is how long the wave is, and the frequency is how close together are those waves. The speed of light, which is given the symbol c, relates these two quantities in this very important equation. C equals lambda nu. Now the speed of light has been calculated many different ways to be 3.00 times 10 to the 8th meters per second in a vacuum. The speed of light does vary according to the medium through which it's traveling. As I talked about, it moves more slowly through air than it does in vacuum, and it moves more slowly through glass or water than it does in air. Viewing light as a wave, it is the space in between the crests that causes the light to be a certain color. Here are diagrams of red and violet light. Which of these colors has a longer wavelength? And which of these colors has a higher frequency? Go ahead and answer that question now. Don't be afraid to rewind the video and look at the pictures again before you answer. Well done. It is the red light that has the longer wavelength and the violet light that has the higher frequency. Once again, we can relate the wavelength and the frequency by this equation. The speed of light, which is a constant, c, equals lambda nu. If I divide both sides of that equation by lambda, I can transform the equation to the frequency of light equals the speed of light divided by the wavelength of the light. So for the red light, which has the longer wavelength, the speed of light, which is a constant, has a larger number for the wavelength and therefore a smaller number for the frequency. Here the wavelength of red light is about 700 nanometers, and this is red visible light. So we could calculate the frequency. We know the wavelength of red visible light is about 700 nanometers. So to do this calculation, it's simply a matter of taking the constant speed of light, 3 times 10 to the 8 meters per second, divide that by the length of the wave, which here is 700 nanometers, which I've converted to meters, and that gives us a frequency for the red light of 4.3 times 10 to the 14th cycles per second. So the meters are canceling out, aren't they? And I'm left with 1 over second per my unit. What does that mean physically? Well, that means if I was over here, looking down at these waves going by, here's my nose, here's my mouth, here's my hair, right? I'm looking at this light, And I counted in 1 second how many times one of these peaks came by my eye. If the wave was moving this way, I would count a lot of times that that peak went by my eye in a second. 4.3 times 10 to the 14 times it would go by my eye in a second. So whenever you're looking at something red, there's a red wave peak hitting your eye 4.3 times 10 to the 14th times per second. Isn't that fascinating? What about violet light in contrast? Well, if I look at the violet light, I see that it has a shorter wavelength, 400 nanometers. So the peaks are closer together. If the wavelength is smaller, here just drawn in smaller font, then that must mean that the frequency is relatively large. Because C, remember, is a constant. C is always the same value. Rearranging that equation again so that frequency is the unknown. For the violet light, we see that we take the speed of light, 3 times 10 to the 8th meters per second, divide it by the wavelength of the violet light, which is 400 nanometers, converted here to meters. The meters cancel, and I see that the frequency of the violet light is 7.5 times 10 to the 14th cycles per second. So again, if I was looking over here with my eye, and I was counting the number of times the peak went by in a second if the light was moving this way, for violet light, the peak is coming by my eye more often, 7.5 times 10 to the 14th times per second. So we have this classical description of light as a wave, and we have a way to compare the different wavelengths of visible light. This description has served us extremely well by allowing inventions such as radar and radio communication. Here I've zoomed in not on radio waves, but on the infrared, visible, and ultraviolet regions of the electromagnetic spectrum. The light that we can see is between a little bit greater than 700 nanometers and a little tiny bit less than 400 nanometers of light. The shorter wavelength, higher frequency light than that is ultraviolet, and the lower frequency, longer wavelength light for that is infrared. And we can't see ultraviolet or infrared light, but there is ultraviolet and infrared light waves in the light that comes from our sun. If you've bought sunscreen, you've probably noticed that it talks about blocking out UV rays. And that is because those rays have higher energy, higher frequency, shorter wavelength, and those can cause greater damage to your tissue than visible light. If we examine white light, such as that emitted from an incandescent light bulb, what we see is a continuous spectrum of all these colors in the visible light. So based upon the experimental evidence, light definitely behaves like a wave. But classical physics could not explain a couple of experimental observations. One of those things that this classical physics idea of light as a wave could not explain is blackbody radiation. And the other thing that had been observed that could not be explained was the photoelectric effect. We've made demonstrations of both of these phenomenons for you to view, so please go ahead and check those out before you watch the next video lecture. The reconciliation of the facts from the photoelectric effect and blackbody radiation with this idea that light behaves as a wave led to the concept of wave-particle duality by Einstein and Planck. Tune in to the next lecture for more discussion about this wave-particle duality and for another relevant equation needed to solve chemistry problems related to light and the atom.